is the greatest force ever applied to move a vehicle. This is the cluster of rocket engines boosting the Saturn vehicle free of gravity, straight up. Saturn is the largest rocket ever produced by the United States. Not a military rocket, Saturn was designed solely as a space vehicle. It can carry multi-ton payloads into Earth orbit or to the moon. And the scientific space exploration by Saturn rockets will lead eventually to placing a man on the moon and returning him safely to Earth. But all the missions planned for Saturn hinge on one essential element of space rocketry: power. Power built into a propulsion system. A propulsion system capable of enormous, concentrated, reliable amounts of rocket power. For the level of propulsion power fixes how far we can go or how much we can do in space. In Saturn, the propulsion system has enough muscle to carry science into deep space. This initial version of Saturn embodies the multi-stage concept. The propulsion system is integrated into vehicle design and function throughout the separate stages. Each stage successively thrusts the Saturn to greater height and velocity. The payload, riding at the top of the vehicle, is finally released in space at the point calculated to perform its planned mission. Here and here are the individual rocket engines grouped in clusters, tied together to function as a single unit. But perhaps before we get deeper into engine systems, we might re-examine some of the fundamentals of rocketry: rocket propulsion and rocket engines. Engines. We're surrounded by them. Auto engines, boat engines, aircraft engines. This is an engine used by the Wright brothers in one of their first airplanes. Like most of the engines we know and its highly developed successors, this is an internal combustion engine. Our Saturn rocket engines are entirely different species. They work on a different principle, the reaction principle. Rocketry, and the Saturn engines, of course, owe a credit to Sir Isaac Newton. In his third law of motion, he stated, "For every action, there is an opposite and equal reaction." For example, in shooting a gun, the action of the rapidly expanding gases moving forward generates an equal force moving to the rear. For every action, there's an equal reaction. In fact, the action of the boy hitting the earth causes a measurable reaction by the earth. Mathematically estimated, a reaction rated at about 1/1,000,000th of an inch in 56 years. However, the rocket engineer confines the reaction he contrives and gains a maximum controlled effect. Power. Like this. If we fill a sphere with highly pressurized gases, there can be no action and reaction. The pressures are equal in all directions, and the gas remains motionless. But if a hole is cut in the sphere, the pressurized gas rushes to escape. Thus, we have an imbalance of pressure in the sphere in these two directions. Similarly, if we fill a balloon with compressed air, there is a greater pressure within the balloon than outside. When we release the air within the balloon, the column of air escaping sets up a momentum going in one direction, and the reaction in the other direction, acting as pressure on the interior of the balloon, propels our little rocket. If we look at a representation of a rocket engine's thrust chamber, we see the same principle applied. Through combustion in the thrust chamber, great amounts of energy are released. Hot, expanding gas escapes through the nozzle throat. Because of the design of the nozzle, the mass of escaping gas molecules is accelerated rapidly. This kinetic energy, bursting from the nozzle exit at supersonic speed, generates an enormous force. From the mass and acceleration of the gas flow is computed a basic measurement of rocket power, thrust. The reaction to this thrust is expressed in pressure against the top of the chamber here, against the sides here, and against the interior walls of the nozzle here, forcing the thrust chamber, and with it, the entire body of the rocket upward. Oh, and one other thing. Many people in the past thought that the rocket required a solid body of atmosphere to push against in order to move. Incorrect. The thrust generated by the engine upwards must overcome the pressure of the atmosphere. As the rocket gains altitude, the atmospheric pressure is reduced. And so you see, not only does the rocket not have to push against Earth's atmosphere, but the net effect of atmospheric pressure is to reduce the rocket's efficiency. These first principles of rocket propulsion are simple. That is, compared to problems of turning principles into hardware, in the form of high thrust, high reliability engines. Intensive development of rocket propulsion technology began only a very few years ago. Many areas of science contributed to the development of rocket engines such as this. And all the existing frontiers of development and production knowledge had to be advanced. In propellant chemistry, to provide new higher energy, safely handled propellant combinations. New materials were needed. New metals, plastics, ceramics, capable of withstanding new levels of stress, shock and vibration, and heat. Fabrication techniques had to be devised, and then improved continuously to manufacture and assemble the new components conceived by engine designers. Then the test programs. When the hardware materialized, component by component, patterns of repetitive testing were developed to prove out the designs and structures, to measure performance, to build up reliability. A cycle of test, measurement, evaluation, and improvement over and over. From this technical evolution came a rocket propulsion industry and the Saturn propulsion system. All rocket engines now used by Saturn have these characteristics. All are liquid propellant engines. Tanks forming the rocket superstructure carry propellants. The engines are bipropellant. That is, they use a combination of a fuel and an oxidizer. The feed system is the heart of engine operation. It delivers the propellants to the engine and consists of a centrifugal pump and a turbine to drive the pump. A gas generator provides a hot gas jet to drive the turbine. The fuel is routed through the many tubes which, stacked together, form the thrust chamber. In this manner, the fuel cools the chamber and protects it from the high combustion gas temperatures within. Oxidizer and fuel, pump fed at high pressure through an injector, meet finally in the thrust chamber. This controlled explosion is sustained evenly by constant propellant flow rates. Full duration of engine operation is about 2 minutes. As we said, Saturn achieves its great power by grouping or clustering individual engines. In the booster stage, 8 H1 engines are mounted in a pattern of 2 squares. 9 propellant tanks are clustered vertically above the engines. 5 contain the oxidizer, liquid oxygen, and 4 hold the fuel, kerosene. The propulsion system is also the means of directional control for Saturn. The outer 4 booster engines upon a signal from the rocket's control computer, can shift thrust direction and thus stabilize the vehicle against aerodynamic forces and adjust the vehicle's course. Upper stage engines are smaller, producing 15,000 pounds of thrust and designed for efficiency at high altitudes. But these engines gain a high energy value by using liquid hydrogen as fuel. Hydrogen permits an energy increase of more than 50% over the more conventional kerosene used in booster engines. However, to use the hydrogen liquid oxygen combination, engineers have had to learn how to handle and apply hydrogen, an extremely reactive element. In its liquid state, it is so cold, it boils at 423 degrees below zero. Scheduled to join the Saturn family of rocket engines later is the J-2, also an upper stage hydrogen-fueled engine rated at a 200,000-pound thrust level. A new engine, the M1, also a hydrogen engine, will produce more than 1 million pounds of thrust. And approaching an operational stage is the Mammoth F1 engine, the largest rocket engine under development in this country. Continuously, engineers of the National Aeronautics and Space Administration are developing the propulsion elements of the Saturn vehicles. Here, held fast in the static test stand at Marshall Space Flight Center, Huntsville, Alabama, a booster section undergoes full duration firing. The 8 engines speak with a unified sound of 1.5 million pounds of thrust. Each of the 8 engines turns out 3 times as much propulsion as the largest jet airliner. Each engine pump, now pulling propellants from the tanks, could drain a railroad tank car in 2 minutes. And right now, the total booster power is about 32 million horsepower. If converted, it would generate electricity for any 3 western states, including Texas. All this has been said in trying to describe, by comparison, the power potential of Saturn. The power potential of Saturn. In only a few short years, the power and effectiveness of flight propulsion devices has progressed from this engine to engines comprising the propulsion system of Saturn. And that system makes it possible to multiply the capability of our first satellite by 1,000 times. The power equation is in balance. Rocket power is the key to greater accomplishments in space. Saturn propulsion systems will provide this power.